Okay, good morning. So, today we are going to start discussing the other part of this course, that is the wave objects. So, we're going to have to talk about the wave nature of light and then hopefully the quantum nature of light and possibly some of them together. But to do this, I would like to go back to what we discussed in the beginning. So I urge you to definitely go back to lectures 1 to 3 that we discussed in the beginning and watch them again and pay main attention to what we talked about plana, right? Plana is what surrounds us. It is not nothingness. This is usually is what we refer to as space. It is not nothing. There is something there, right? It's just non-massive. It does not have a mass. But as you may have heard before, um, there is something that is bending and warping, right? There must be something there to bend because of gravity, and that something is plana. So you have studied about mechanics, you studied about electricity and magnetism. So there is another type of quality in objects called charge, right? Which we often indicate by Q, and this comes in two varieties, plus or minus. And these plus or minus varieties are essentially they're determined by the way this charge interacts with this plana, right? Because it is ultimately through the plana that interaction between two charges takes place. Let's see how. For example, if I have a positive charge placed here, it's going to disturb the plana that's immediately that it is immediately in contact with, and that plana is going to disturb another part of the plana that's next to it. And as you're going outward, the intensity of this disturbance is decreasing, right? And now if I have a similar charge here, out here, a similar charge, then this force is these changes are such that this charge is repelled away, right? But if this charge, for example, if it were negative instead of positive, then it would be attractive force, meaning the planar changes in such a way that two negative charges or two positive charges will repel each other, but two negative or two negative and a positive charge or unlike charges attract each other, right? So basically, from there you use the Coulomb's law, and then from Coulomb's law you derive. So you start with Coulomb's law in electrodynamics, and then you go on to Gauss's law, where you define something called a flux, electric flux. I'm only giving you an overview here. You should already know this. It's a prerequisite for this course. There is not sufficient time for anybody to cover all aspects of light in one semester, right? So Gauss's law, Coulomb's law, these are electrostatics. That is, the electric field, it's not, the charge itself is not moving, right? And once you begin to move the charge, there are other effects that come into picture, right? Then you look at currents, right? Flow of charge, right? And then another thing that comes with the current is now you see another kind of field in addition to the E field, that is the electric field. You begin to see the B field, magnetic field, because of the current. And in general, if the electric field, if I have a wire, if I have a cylindrical wire, and let us say the current is flowing up this way, you could point your right thumb along the wire and roll rest of your fingers around the cylindrical wire, so you can have your thumb pointing up and the rest of your fingers are going around. That gives you the direction of magnetic field. So the magnetic field is going this way. And this magnetic field always happens in closed loops. For example, here it's in closed loop. And then you see that although this magnetic field, much like how electric field has plus and minus Q, this magnetic field has north and south poles, but because the magnetic field lines, they were always closed loops, it seems impossible to separate them experimentally. And so it so happens that that itself becomes the Gauss's law for magnetic field, that you cannot separate del dot B is equal to 0. That is, you cannot separate north and south poles. You cannot find magnetic monopoles, right? And then there is the question of changing the magnetic field itself in time. That is, now you're going to change the flowing current in time. So you have basically two different types of fields: electric field that comes from the charges, magnetic field that comes from a moving charge, and electric field that's varying in time because a charge is varying in time, charge is moving in time, and a magnetic field that is varying in time because a current is varying in time. And so if you have these two time varying field over a period of 200-300 years from Newton to Maxwell, with important contributions from Ampere and Oersted and mainly Faraday, we understood that electric and magnetic fields are so closely linked to each other, and we can make one type of this field from another. For example, if I change electric field in time, somehow I can get a magnetic field, and if I change magnetic field in time or space, somehow, but rather by saying the field itself, I say the flux. By changing the flux, somehow I can go from one field to another field. And then there was Hertz, not the car rental guy, but the experimentalist Hertz. So Hertz basically, and the one whose name is used for the frequency Hertz, experimented, and he showed that now this the four Maxwell equations, right? Maxwell basically summed up all the variations of electric and magnetic field. Maxwell summed them up into four equations. We will go into more details later, right? But I'm just trying to give you an overview. So using those four equations, it's just pretty straightforward to derive a wave equation, which is a second order time derivative related to a second order space derivative. But it is essentially describing a wave, right? And so that's the discovery that Hertz made, that light is an electromagnetic wave. That means light basically has a component of electric field and magnetic field, and they're perpendicular to each other. So electric field is oscillating up and down here, and magnetic field is oscillating. So this is the magnetic field, this is the electric field. So here the electric field is oscillating up and down, and magnetic field is oscillating back and forth, right? And magnetic field in its magnitude, as we will see later, is much weaker, 10 to the power 8 times weaker at least, than that of the electric field. So most of the time we will only consider the electric field, effects of electric field, and whenever we understand the effects of electric field, then we can just simply add in the effects of electric field by just using a constant, because it's B turns out to be E by C, where C is speed of light. So just using that, you can substitute the effect. So whenever we study light as a wave, we will just use electric field. So to represent a wave, as you can see, it's a sinusoidal wave, right? So when I say a wave, here you have to be very, very, very careful about a couple of things. First thing, what is a wave? When I say a wave, it is a wave in a medium, okay? So like sound is a wave, it's a disturbance. A wave is a disturbance. It's disturbing a medium. Sound is a wave that is disturbing the medium, for example, air. So it's causing pressure, compressions, and refractions in that medium. Similarly, if I take water wave, it's a disturbance in water. So similarly, light, what is the medium? Right? You might say light does not require a medium. You might be right, but don't make the mistake of doing that, because light does require a medium. It just happens to have no massive substances in it, right? Recall that plana or space is not nothing. It may sound like a silly philosophical note, but space is not nothingness. So it is incorrect to say light does not require a medium. Light is a wave, and it is in space, and space is not nothingness. It is something. That's why it is bending and warping. So light is a property of plana. Plana is basically extension, the first property of any material thing. This is nothing philosophical or metaphysical. It is just a non-massive body. It's non-massive body. Space is non-massive, that's all. It's non-massive, still it can bend. That's what Einstein showed, that Newton foolishly left out, thinking that information can be transmitted at instantaneous speeds, that from sun to moon or sun to earth, information can go at instantaneous, at any speed. But Einstein showed that there is a limit, and that limit is that, Einstein didn't show that there is a limit. Einstein basically found that the space basically is changeable by itself, and it is not Euclidean. Euclidean meaning flat space, like a Newton thought. It is non-Euclidean in the sense that it can be bent around. That's what Einstein figured out. And this light exists in that space. Why am I saying that this light exists in that space? Because light is nothing but electric and magnetic fields. So if I have a charge here, a positive charge, where are the fields from this charge existing? The fields from this charge are existing in the plana. They're perturbing the plana, they're perturbing the space, right? The magnetic field also exists in the space. So electromagnetic fields exist in the space, or light exists in the space or plana. So light is a property of the plana. right? So the velocity of light, comes out naturally from Maxwell's equation, very beautifully actually, and that's what gave a great experimental confirmation as well. And roughly, if you write it, it is 3 into 10 to the power 8 meters per second, right? And you can reduce it, of course, by putting into a material, right? So if I put it into a piece of glass, let's say, if I put it into a piece of glass, right, of say refractive index 1.5, what would be the velocity of light here? Right, you know that velocity of light is C over n, right? C over refractive index. C is 3 times 10 to the power 8. This is glass. So inside this glass cube, light would have 2 times 10 to the power 8. So by using any material, right? This is massive material. Any material that has mass, right? That has a refractive index greater than 1, you can reduce the speed of light, right? So let me now also talk a little more about something else very quickly in this lecture, because I don't think we'll get a chance to finish that in this course at all, and it is way too advanced for this course as well. But because light is such an important topic, I'd like to address it. Recall that in our first lecture, we talked about the de Broglie wave-particle duality. And when I discussed this wave-particle duality, we had the relationship P is equal to h over lambda. I hope you recall it. So when we said that P is equal to h over lambda, what did we mean by that? For example, if I have a nice tennis ball, right, that is moving with some velocity, so it has some momentum, okay? So then I can, by using the de Broglie relationship, I can put P is equal to h over lambda. Then I can say, okay, the lambda of this tennis ball is h over P. So from this, the usual interpretation is that as if the tennis ball is a wave of wavelength lambda that is spread from negative infinity to positive infinity all across the universe. But you know the tennis ball is here, right? You know the tennis ball is here, so how can it be that it is spread everywhere else? So even somebody like Heisenberg was foolish enough to say that I have disproved the principle of non-contradiction, right? Because that's what you're doing here. So recall that this is not the right way, that this lambda is lambda of the wave packet. This lambda is the lambda of the wave packet. In quantum, we don't get the exact values. What we have are the average values, right? So then you're modeling this tennis ball as you're modeling it as packet of waves that has an average mean wavelength of lambda. So you're taking several different wavelengths and mixing them up, and to make an envelope that gives you a wave packet. And it is this wave packet that's moving with a group velocity of v that gives you an average momentum of p. That is the right interpretation, right? So this is called first quantization. Why is it called first quantization? Because again, if you recall, please go back to lecture 1 and 2. I posted a video in those lectures. I mean, I posted the lecture itself as a video, but within that video there is another link, another video that was showing a Hitachi experiment on electrons in a scanning electron microscope. It's a double slit interference experiment. So essentially in that experiment, if you recall, you have a double slit here, and there is a lab 6 lanthanum hexafluoride electron filament, right? And the screen is on this way, and as the electrons came out one by one, one went here, one went there, one went here. They were random, but they appeared so. And after millions of electrons, they started forming these patterns, right? After so many electrons, they started forming the fringes. And then I mentioned something to you. I don't know if you remember that, but I would like to re-emphasize that again. I know this is not a quantum class, but while discussing light, this is important. So there, in this case, we're looking at particles, whether it's a tennis ball or electrons. We're looking at different particles. We're looking at, in this case, for example, in the case of the electrons, we're looking at several millions of electrons impingent on the screen, and after having looked at these millions of electrons, I'm able to see a wave-like fringe pattern, a dark and a bright fringe pattern, after having viewed millions of particulate-like electrons. And from there, I'm deriving a probabilistic wave nature, right? So when I say wave nature, this is a probabilistic wave nature, right? This wave nature is not a wave nature like electric and magnetic fields exactly, in the sense that electric field is a physical thing, in the sense that it's a property of the space. If I have a charge, electric field is a physical thing that becomes physical property that comes out of that charge, right? Whereas the probabilistic wave function you're writing psi, right? A lot of people like to tell you, treat it like electric field, but electric field is a real thing, that if I have a charge, the charge has, in objective reality, the charge has an electric field. Right? This wave function for a particle is your statistical description. It is not you are describing whatever these fringes are to describe these. You're creating this. You're using this as a crutch. You're using this wave function. It's not a property. Wave function is not a property of an electron. Like how electric field is a property. Like if I have a charge, it has an electric field. Like that, it is not an electron has a wave function. No. A wave function is something that we are using to describe the behavior of these electrons. In any case, by looking at the behavior of multiple electrons, which appear to be particles on the screen, I am coming up with a probabilistic wave nature, probabilistic wave function. So again, as I said, this is called first quantization. So in case of first quantization, there is a real particle. Real particle, meaning the particle is real. So there is an electron that's coming out of lab-6 filament and falling on the screen that you can see in the electron microscope, right? So you can see it. I mean, insofar as you understand the electron microscope, if you get into the philosophical details of can we ever know anything and can we ever see anything, I would be happy to debate on those issues on a separate note. But here, you as an experimentalist, this is objective reality, because irrespective of whether you do it in Clemson or I do it in let's say in Australia, or somebody else does it in Japan, or an alien does it in Mars, it's going to give the same result as long as the experimental conditions are the same. Okay, so that's the objective reality, right? So there is a real particle. So the objective reality there that I'm talking about is that if this lab-6 filament or a tungsten filament is heated, then an electron is going to come out that is independent of me. So that particular particle that is coming out, we're looking at that particle. So that particle is a real particle, it exists, and by studying the behavior of several such particles, we are understanding how things are behaving. So we call that as first quantization. I would like to make another note here. When I said that we are studying these particles here, of course we are studying many particles. So you can consider all these many particles as a statistical ensemble. But when you study quantum mechanics, there is another ensemble interpretation. That quantum mechanical ensemble is not many particles. That quantum mechanical ensemble is multiple duplicate copies of the same particle. Anyway, you'll get to know that, but bear in mind that quantum mechanical ensemble is not the traditional ensemble. So when you hear that word, if you are in a quantum class and if somebody uses it, make sure that you get the right interpretation. And there's a book by Ballantyne that's excellent for that. So anyway, the take home message, the main message that I would like to tell you is things like electrons that are really seen as particles can be treated as waves in terms of their probabilistic nature, and this is called as first quantization because they are real particles being treated as waves. Now, other way around is the second quantization. So, as you can guess, in second quantization, you see a thing as wave. Now, you have to treat this wave as a particle. Okay. What is one of the waves that you know that we are studying? One of the waves we know that we are studying is an electromagnetic wave or a light wave. But why did the need arise to treat it as a particle in the first place at all? Right? A lot of people will tell you that it is the photoelectric effect. It is incorrect. Photoelectric effect does not require the quantization of light. Photoelectric effect requires only the quantization of the materials. It does not require quantization of light. So It came because of something called, even prior to the photoelectric effect, there was something called UV catastrophe. You can find this in many textbooks or even online. So what this means, I'll try to explain it very briefly, right? And you should know this. This is very, very important. For example, now, let's say we have a box. Let's say we have a box. Assume that this is a perfect box, that no light can leak from it, right? No energy can leak from it. Imagine that it is in thermal equilibrium with everything else, and it's leak proof. So it's what we call a black body, right? So now if you heat it to a temperature T, and you can poke a tiny hole here, and you can collect the spectrum of the light that is coming from here and see what light is coming out of a black body, right? So when you heat up things, what happens when you heat up things, when you heat up molecules? When you heat up molecules, molecules are essentially like springs, right? Their bonds act like springs, so they're like tiny little springs, right? So they vibrate. So this half cake square vibration. So to calculate how much total energy I would have, I could calculate how many modes would there be in my box, and without having to go into my into detailed calculations, I'll just tell you that if you calculate just from simple classical mechanics point of view, you would get kT by 8 pi by c cubed nu squared d nu, where this is the frequency. So for each frequency of vibration, there would be these many modes. Okay, so for each frequency of vibration, there would be these many modes. So so as you can see, it is going as nu square. So if you were to integrate from 0 to infinity, this goes to infinity. That is, even at basically, even if I heat it to a finite temperature, it should radiate like infinite energy. So this is basically, you are trying to get something like, emulate something like sun. That is, you have a body, right? You are trying to get the radiance, right, out of it. So you heated it to a temperature T. From whatever classical electrodynamics we knew at that point, if we followed the classical electrodynamics we knew at that point, then this temperature T, because of this temperature T, any molecule had an energy k bt, where b is the Boltzmann constant, and because of the temperature T, they oscillated like springs, and because of that, energy was emitted. That is the electric dipole radiation, and that you could calculate how much it would be at each frequency using something called the Rayleigh-Jean law. And if you did that, basically they were getting infinity, which didn't make sense. So that's when Planck came along, Max Planck, and said that the number of modes for a given frequency is not this, right? It's not necessarily go to this, right? He put in his quantum mechanical expression, right? And the main thing was that he basically said that the energy here is quantized. It is not continuous. You cannot have any and every frequency, right? You cannot, sorry, you cannot have any and every energy. And he basically said that that energy is quantized. So he said that energy E is equal to h nu is quantized. So that's where the quantum came about. So when he did that, what he meant to say is that when you look at quantum electrodynamics, we say it is a photon is a virtual particle, because you have light is ultimately, like I said, it's an electromagnetic wave, right? That's propagating in space and oscillating in time, right? You are just assuming, you're creating a being of reason, in the sense that you are thinking to make things, to make your math easier for you. You are creating a virtual particle. There is no real particle. It's a wave, right? This is electric and this is magnetic fields. You are creating a virtual particle that makes things easier, right? And using, for example, when you do the quantum mechanics, you will study quantum mechanics, or if you have already studied, you will study, or some of you may not study, so forgive me if I am going overboard. But the idea here is that when you study quantum mechanics, you will study something called a simple harmonic oscillator, right? Simple harmonic oscillator is essentially a springs, right? Half kx square. After finishing that, you will look at it in a different thing called the number representation. That is, instead of looking at the wave function, what is the probability of finding a particle at one particular location, right? So if I have space like this, just consider this space. I could think about it in two ways. One way is, what is the probability of finding one particle? I have 10 particles, right? So I can think about it as, what is the probability of finding particle 1 at any point in this space? Call it wave function of that particle, right? Similarly, I could have wave function of second particle, so on and so forth. Or I could think about it another way. That is, okay, at this point, what is the probability of finding particles 1 through 10? How many particles do I have here? How many particles do I have here? I'm counting the particles instead of the probabilities. So that's the number representation. So in the number representation, you're creating these virtual quanta. You're assuming these virtual quanta. These don't really exist in the sense that like the existence of a tree or existence of a physical thing. It's a virtual quanta. It doesn't mean that it is it is your paranoia either. Okay, so it's a virtual quanta. So photon is the virtual quanta. Okay. So that's where the second quantization comes from. So Einstein's contribution to the photoelectric effect actually doesn't necessitate the quantization of light. The quantization of light, quantum electrodynamics, comes not from photoelectric effect. Okay, but once you have quantized, like I said, in case of a simple harmonic oscillator or a spring, right, you can think of the number representation. So that's what the quantum field theory and quantum electrodynamics do. They view your reality, your physical reality, as if your entire, if I take out everything, right, your computer, your chair, your desk, every physical thing away from the reality, and there is just this vacuum, just this 0 point field, just nothing else, just the empty space, right? Just, I shouldn't even use the word empty. It's just the plana that there is, right? Nothing else, right? Just the vacuum fluctuations that there are, right? Then those vacuum fluctuations are also basically quantum fields that are like harmonic oscillators. So, or in other words, like Feynman likes to say humorously, like, your world is a mattress company, right? Because it's made up of simple harmonic oscillators. So we will stop here. In the next lecture, what I would like to do is I would like to use some ray tracing softwares to provide you some hands-on experience with ray tracing. And yeah, so we'll stop here. Thank you.